It's now recording. Okay, cool. Just make sure we should all be good. All right, hey guys. Welcome to this small workshop I've put together to kind of help people become a little bit more familiar with Simulink and some of the tools within Simulink, in particular Simscape Multibody. It is a kind of a collaboration with CU InSpace and CSES because we were planning on running kind of an internal training anyways for Simulink, and you know, lots of people need help with it. I know I needed help in third year, so that's kind of why we threw it together. Thing one, I've been asked to record the workshop. It's just going to be me. I'm not recording computer audio or video. It's just the slideshow and my voice, so you guys don't have to worry about that. Slides are going to be available afterwards in the InSpace Discord server and also in the general chat of this Discord server in PDF format. What you'll need, you don't need this for the workshop. This is just if you want to actually like use the things that are shown in the workshop. Computer that can run MATLAB well. It's kind of graphics intensive. You'll need, you know, obviously a copy of MATLAB itself, which you get licensed for free with Carlton. Simulink, which installs by default with MATLAB, and Simscape Multibody, which usually installs by default with Simulink, but it can also just be downloaded from the add-ons tab in MATLAB. It's I show how to get to it in just a sec. Oh, and who am I? In case you guys don't know, this is me. I'm an aerospace stream D, and the only thing that matters is I know some things about Simulink, and that's why I'm doing this. Yeah, I also on CU InSpace lead the payload subteam. Start with MATLAB, okay, from the ground up. If you're not familiar with MATLAB, but you want to use Simulink, all you need to know is that you use it to run and interact with Simulink. It's useful for a lot of other stuff, but you know, it really here I'm not going to go hugely in depth because you physically can't. You can spend a lifetime learning more about MATLAB. But just really brief overview. Navigation window is shown at the top of the screen there, and this kind of has all the buttons you can press to access different stuff. So while you're editing scripts, you have the run button, run in advance, you know, a couple debugging tools, all of which aren't particularly important, which I'll get to in a sec. The standard home tab lets you make a new script and open and load new scripts that you can call upon, which are actually really useful. Yeah, and you can also import data from, be it like sensors or like from Excel, or if you're getting like lab data, you can import it into your workspace. And you can also save your workspace, so if you're running simulations and you want to save it for later and open it back up, you can just save just the variables that way. And I find is like really convenient to just pull up just the variables. Okay. Yeah, and then also if you go to apps, you can get more applications and packages. I have a lot in my MATLAB. Highly recommend PID Tuner if you don't have it by default. If you take control systems, because it's just a really good tool. Oh, and of course the Simulink button, the main big reason we have this in the first place. The workspace is on the right of MATLAB. It just displays all of your variables. You can import like software-defined radio data. Oh, I went way too fast. Oops. And you can also export stuff to here from Simulink. So even though it's in MATLAB, you still use it to interact with Simulink. Just like how if you're typing in the MATLAB console to call a variable, like if we're to like, I have in the command window here, storing B as a matrix, you know, G as a transfer function. I think X is just a value. These can all actually be called from MATLAB, even though you're using it in Simulink. And then the command window is basically just faster than clicking buttons. You can run any script that you've written before by calling it in here. If you save a file called like myfile.m, and then you just type myfile dot, or you just type myfile in here, it'll run the script myfile.m. Okay, running Simulink. Disregard the mixed up arrows. Yeah, so first way to do it, you can click the Simulink button. That's pretty easy. Or you can just enter Simulink into the command window. I like to do that because it makes me feel cool, but it's more button presses. You also want to make sure that every time you're editing a MATLAB file, a Simulink file, or anything related to MATLAB, that you have it open to the folder that you want to work in. Here I had a folder called Simulink Workshop that I made sure it was all done in, and that way I could make sure whenever I was saving stuff from Simulink or to Simulink to the MATLAB workspace, I knew it was all going to be going to the same place. If you don't have that specifically open, like you're not going to be able to it's not going to be able to find it. Yeah, so that is very overview crash course of how to navigate MATLAB and why it's useful. And by the way, guys, like if I'm being unclear about anything, just let me know, because I don't know. I haven't run this before, so I don't know if anything's unclear or not. But please ask questions, because okay. PowerPoint. What did I do? That's not what I meant to do at all. Is it still? Oh, it's still streaming. Excellent. Okay, that was weird. Right. So when you open Simulink, this is the window you're gonna get. You're gonna have all sorts of options. I have a bunch of other block sets kind of installed, so it's gonna want me to try making different types of projects. We just want to start with a blank model. That's gonna be like just blank workspace. Nothing's there to start with. When you get there, you're going to have kind of this window here, and there's going to be just a blank white space, this toolbar at the top. To get those blocks, you're going to want to go to the library browser. And these are going to have all your Simulink blocks. And what a block is, if some of you haven't seen block diagrams before, we're going to see them in a sec. But they're little commands, effectively, that you can plug into each other in order to run the simulation. Okay, once you're already a little bit familiar with the blocks and you know what they're called, you save a ridiculous amount of time by, instead of using the library browser, you can just double click the workspace and type in the block you want. It goes way faster. Yeah, you'll also see in the library browser all the different plugins you have installed. So for me, I've got like, aerospace block set, control system toolbox, save all these extra stuff. By default, you probably only have Simulink and maybe Simscape. The only ones you need are Simulink and Simscape. If you don't have Simscape or Simulink, the way you end up getting that is you go to the apps window, you just click it, and then you can just search for Simscape. It's really easy. It's all within the program. Yeah. Opened another PowerPoint on me. There we go. Okay, so here's kind of, it feels like we really went from nothing to straight up maximum level simulation with just one slide, right? It's just to kind of show an example of some of the blocks you'll probably see pretty frequently in Simulink. First one here is a step function. And the way this works, by the way, I haven't really given a clear overview of what exactly Simulink is for people who have legitimately never touched it before. Effectively, it's going to be running a simulation where it's not going to be outputting a single value, but it's going to run through a period of time. And it's going to create a series of numbers throughout that time. That's what the simulation is. So what happens then is we run it for 10 seconds, it says here, and our step input is effectively, the input is from negative infinity to 0 seconds, it's 0, and then from 0 to simulation time, it's just 1. That basically means when the simulation starts, step input starts and gets fed into the system. So it's really, really common to use step inputs as kind of your basic, like, this is what you use as your input for your simulation. There are other ones, but that's the most common. This one's pretty straightforward. I think you can figure out what this does. It takes whatever this value is, and it adds it. It takes whatever is coming off of this value, and it subtracts it. So if you, in discrete time, you have 1 coming off of here, and you've got like 0.5 coming off of here, it's gonna output 0.5 out of here. Gain, it's literally just gain. It's just a multiplier. Transfer functions, this was a block that took me too long to find. As soon as I found it in CISC 3600, I think, I saved a good amount of time. It's literally just a transfer function block where you can just type in your transfer function, the numerator, the denominator, and it just acts exactly like a transfer function would. I'm pretty sure this specific one is just like a compensator. It's not like an actual controller. I was about to get to that. Yeah, I was about to get to that. Yeah. Yeah. What I was basically going to say is if you don't know what a transfer function is, not going to matter. Yeah. I was getting there, Brendan. Yeah. It's like a function you can get when operating in the frequency domain, which you get to by applying a Laplace transform to a second or greater order differential equation. And you get there by taking classes in 3rd year. That's honestly like the best explanation I can give. Knowing what a transfer function is not vital to the rest of it, so it's not that important. Okay, integrator. This one is just like it integrates. It's a transfer function of 1 over s. But an easier way to just describe this physically by looking at it is the numbers come around, and it kind of holds your numbers here, and then it kind of adds up the previous signal that's coming in. It's integrating. It's adding it up over time. And then this all gets put into 2 different outputs. These are pretty common outputs that you see when you're working with pretty basic Simulink. The first one is scope, which I actually have them both on the next page. But doing an output to workspace, basically, like I said earlier, throws it in the MATLAB, where you can just kind of work with it in MATLAB. It's going to be a weird variable type called a time series, so you need to do one additional step to convert that to either a matrix or an array or whatever you want to do with it. But then it's in MATLAB for you to use, and you get to assign the variable. The scope, on the other hand, looks like this. A scope you feed a signal directly into, and that's kind of how it looks. And it shows you over the period of the simulation what that signal looks like. So if we go back to here, this step input of 1 goes through. What this scope sees over time is this number here. It goes up to 0.5 over the 10 seconds. So again, if you haven't taken CISC 3600 or equivalent courses or feedback control system stuff, it's going to be completely foreign information to you. But if you have it, it's typical. That's what you come to expect. Okay, so that's the first way. The first way is to use a scope. They can have multiple inputs if you want. It'll have like different colors for the different signals. You can also use what's called a mux, which I'll talk about it later in the slideshow. But, there's another way to do it, and it's a bit of a faster way for kind of like less permanent solutions. There's a thing called log signals where you can just kind of click on any of the arrows you want to watch. You click log signals, you run the simulation, you click the button called View in Data Inspector, and yeah, and then they just kind of show up in the Data Inspector. And either one you can kind of use in MATLAB. You can process afterwards. Just quick tips. I forgot to write this one down, but this one's great. You can copy any block by holding right click and dragging. That's just, it makes it really fast too, if you're making copies of a thing. Control R, Control Shift R to rotate a block left or right. You can hold and drag to create a subsystem, which is basically like a mini block diagram instead of a big block diagram. It's stuff to make it more organized. You can label all your signals by double clicking them. For example, if you have a simulation and one of your signals, this corresponds to like first derivative of x, you can click on it and label dx. And that way, when you're looking at it in your in your log signals here, it will actually say this is your dx signal. And then finally, you can insert boxes, images, and captions. You can keep them looking nice and user-friendly. Okay. So, one more thing, and then I'll double check everyone's caught up with me, because this is all just like basic, Simulink stuff. Make sure you're all caught up to speed. Or at the very least, you have like some of the core information that's kind of important. Model configuration properties. This stuff's pretty complicated. I don't quite understand it. I know that the simulation time is like how long the simulation goes for. And I know that the step size, if you have a smaller step size, it's going to be a smoother simulation, but it'll take longer to do. It also might be more noisy. But if it's a larger step size, oftentimes, objects might clip right through each other. You're just not going to get the data you want at all. So if you ever have that happening, like objects clipping through other objects, first thing you should do, decrease the step size. Yeah. Okay. I've like, noise is like, it's effectively like numbers that just come out of nowhere and you don't want. When you get to computer simulations and reading sensor data and stuff, you're never going to have a 100% accurate result. There's always going to be some bits that are slightly off. But when you get to really, really small periods of time, you're eventually going to get where that your entire read for that period that it's been reading is just noise. It's just wrong. And so if it takes that entire just wrong, it's going to kind of throw off your whole simulation a little bit. It's a lot like how when you have like a wireless communication like antenna, right? You want to have a good signal to noise ratio. I don't know if this is like that helpful. The reason being like noise when you've got a wireless communication is going to come from like the ionosphere. It's going to come from like just the atmosphere, other electromagnetic interference, just straight up resistance in the antenna, all that stuff it's going to come from. So you want to make sure that you're reducing the noise. And it's the same thing, just like digital in a computer. Yeah, it's entirely computer simulated, but they still can have problems, which is kind of funny. It really does. Okay. Yeah. So that was Simscape, or that was Simulink, kind of in a nutshell. I can answer, other questions on Simulink and stuff, but the main thing we really want to focus on is Simscape Multibody, because you don't really need to have a good understanding of like how these even work in order to understand how to use Simscape Multibody, because it's really visual and it's really intuitive, and it's actually like really, really useful. Yeah. Okay. So, oh, by the way, I don't think I mentioned it, but that first kind of example I showed of the second order system, just with a bunch of different blocks, I did put that in the text channel if anyone was interested in playing around with it. Okay. So, Simscape Multibody. It's a plugin. It just adds a bunch of blocks to Simulink. And what it does is it does a bunch of the hard simulation math for you. I know if you're in dynamics, or especially if you're in dynamics of machinery, it's a little complicated to kind of do all that like synthesis for your linkages, right? Yeah, but if you roll this up in Simulink, if you're just designing a linkage for fun someday, like I do sometimes, instead of doing that, you can make the CAD files, or you can just make the blocks within MATLAB, and it will kind of do all that hard math for you, to the parameters, and it outputs a dynamic simulation. Okay, here's kind of an example of one thing I've done with Simscape recently. Is I'm volunteering with the satellite lab, and one of the things we had to do was do kind of the sizing of a reaction wheel to make sure it would have like enough inertia to be able to turn the satellite around. A reaction wheel is basically like a bit of mass that you spin one way to cause the CubeSat or the satellite to spin the other way. And so we wanted to make sure, are these numbers that we came up with for these values, are they actually going to work? We wanted like just like sanity check to make sure that our values were all going to be fine. And so I whipped up this simulation here, and this is also in Simulink, by the way. The blocks look a little different. Some of them are the same. You can see the scopes. But like the previous one, we have all these kind of bluish blocks, and these are all added by Simscape Multibody. So they allow us to kind of make these 3D structures, put them together, connect them with joints, directly input torques or forces or moments or whatever, and then directly observe the outputs much easier. So, oh, and also, yeah, you get 3D simulations of what happens here too, which is always like, that's my favorite part. But you can see we ran the simulation of, I think it was speeding up the wheel and then slowing down the wheel for 15 seconds. And yeah, we wanted it to do at least 180 degrees in doing that, and it did 190 degrees-ish. So we're like, yeah, that's good enough. That's a big enough wheel. And the other advantage with that is because it's integrated with MATLAB, like I was saying earlier. We have these workspaces. Where is it? There. We have these workspaces with all these variables, and because we keep calling on those, we wanted to test a few different materials for wheels, and so to do that, just go into MATLAB, the console, change the name of the variable, and all of a sudden, instead of using stainless steel, we're using brass, and it works just as well. So that's kind of like where I personally use Multibody. I find it really, really convenient and also really cool. Yeah. So before I get into, I just want to keep checking, because sometimes I can get a little bit carried away. Anyone got any questions so far? It's really hard to give a proper introduction to Simulink just because, if you haven't taken CISC 3600, it's going to be totally new stuff. Okay. So let's get into Simscape Multibody. So like I said here, if you're familiar with the previous MATLAB tools, you might, or rather Simulink tools, you might not be super familiar with these ones, but they're actually pretty easy to understand. So start with things every mechanism needs. These are things you need to have or else your simulation isn't going to work. Your world frame, and this is just a universal reference point. Everything else can kind of call back to. You need a mechanism configuration block, which basically tells Simulink, hey, this is a mechanism. And you need a solver configuration block, which basically tells Simulink, hey, you need to solve this. It's like, it's pretty basic things, but they're just necessary for the simulation. They also do things like they tell you what gravity is. Yeah, stuff like that. You'll also notice, unlike the previous simulation where we actually have signals going from block to block, these are actually not connected by signals. They're actually connected mathematically by something called reference frames. And if you've taken orbital mechanics, Aero 3240, it might be kind of familiar to you because it actually works really similar to how the rotation matrices and reference frames work in that class. You have, with each kind of block, with each kind of frame, these kind of reference frames. They've got like little like triangles on the end. That's just to say it's a reference frame. So you have different blocks to kind of represent where these frames are. You have a reference frame, which is literally just a frame, nothing else. You can just connect stuff to it. You have rigid transform, which is effectively you're applying a transformation to it, be that a rotation, like a rotation matrix, or an actual translation to physically move an object. Those are both handled by rigid transform. Translation sensor is like rigid transform, but kind of like backwards. In that, if you are to connect the two ends of a transform sensor to something, it's gonna, rather than move it, it's gonna see how far it's moved. Another thing with these and a lot of the other things, B and F basically means literally just back and front. So basically the back you want to point towards the world frame and the front away from the world frame. So that's just the orientation. Otherwise your transforms are going to be backwards. Solids. These are definitely like the thing that makes Simscape Multibody what it is. You literally put them in and they're just building blocks. They've got so many different shapes. You probably want to keep them as simple as possible. A lot of the times I'll use like 3 or 4 rectangles or cylinders if I have to. But there are options. I mean, you can straight up import CAD files, which we're actually currently doing with CU InSpace. Yeah. And so when you import them, this is kind of what they look like. You can give them like the dimensions. If you want to open another port that exports its geometry, which allows things like collisions and stuff, which is actually like the next thing I'm gonna show, which I've got a couple files for. Then you would click this, export entire geometry, set its inertia and mass and stuff, change the color, create another frame on this solid. And this part's actually kind of important, is how to create new frames on solids. Because each frame can be used as its own attachment point. Because if we look at the default blocks, we look here, it's only got one attachment point, and that's by default at the center of mass, which is not super useful if you're trying to make like a linkage or something. You want your links to be at the end of each of the boxes. So, when you're creating a new frame, you want to make sure it's with respect to the geometric feature you want. Most convenient, you put it at like the end of whatever your bar is. You also want to be careful with the orientation of this axis. And that's because there are some joints that are only going to work along certain axes, which I'll get to in a second. But you don't want to mix up your X, Y, Z axis because you do need to like constantly reference them to make sure your your link is not moving sideways as opposed to up and down. Joints, okay. So if I go back to the very beginning here, not too many joints. Literally just two. It allows the satellite to spin with the world, and it allows the wheel to spin with the satellite. But there are a lot more ways things can be connected. I mean, you learn like first year, just like the types of joints things can have. And they've got like pretty much every single one you could imagine. Yeah, you use them to literally just connect two frames together. And that joint is basically going to allow kind of degrees of freedom between the two joints. So if you haven't taken dynamics of machinery yet, a degree of freedom is effectively a direction that something is allowed to move. And by default, you kind of have six, those being, the X, Y, Z direction, and then the rotation normal to X, Y, and Z. So that's like three prismatic directions they're called, or three, not rotational, the other one, revolute, degrees of freedom. But you can define all of those with these joints. So a 6 degree of freedom, just gives you free space. The object's able to move anywhere. Whereas a revolute, you're only going to be able to rotate. And that's kind of similar to the transform like I had up here. Except rather than being a direct cause to move it, it's just a restraint, meaning it's not going to move in any other direction. It's only going to be able to move there. And the other good thing with that is this is actually where you can put inputs to add things like torque, add things like force, add things like speed, and also you can like sense movements and stuff. But we're not there yet. So, first thing that I threw together as a pretty nifty little simulation. I've got two different versions of it in the workshop channel. If anyone did want to run it themselves. One of them is just the system with nothing added. One of them is just the complete system when it was done. But here's what we're working with, okay? I set up a system where there's no gravity. It's just two spheres in 6 degrees of freedom. We set up a spatial contact force. And we set them up 5 meters apart. They're 1 meter diameter balls. I'm pretty sure this is like extremely similar to one of the dynamics projects last year. So it might look a little simpler to some people. Yeah. So what you can do, mechanism configuration, no gravity, simplifies the system. Honestly, I was being lazy. That's why I did that. It technically uses less computing power as well. And then also you want to make sure you're clicking the export geometry on both balls because that lets you connect it to this spatial contact force. I'm sharing my PowerPoint, yeah. The PowerPoint has the Simulink on it. Wait, are you guys aren't able to see my cursor, are you? No, I honestly like took screenshots of literally everything I'd be able to show in Simulink. Because some people said they couldn't make it, so I wanted to give them all the information. But thanks for letting me know. Yeah. So export the entire geometry. connected by the spatial contact force. This is just like one of those special blocks that's included in this package. There are a couple more. I'm actually going to double check what the other ones are because I've never... Yeah, there's gravitational field, there's external force, internal force, inverse square law force, and there's spring and damper force. So, yeah, spatial contact is probably the most like frequently seen. I mean, you do that in Dynamics 1 pretty much right off the bat. So, we got two balls here. They're all set up properly. We run the simulation, and we put the balls, and they're there. But nothing happens, because we specifically removed all the external forces. That way we can analyze them kind of just on our own. So, to do that, we need to add some motion inputs. And you do that to the joints. So if I go back here, where I have these joints, these 6 degree of freedom joints, you can go into them, and you can specify for each direction specifically what you want that actuation to be. I selected to have an input based on force, and then being provided by an input signal, so I could show something else in a sec. Yes. Yeah, and that'll be in the X direction, because you want to select the correct direction. This is why you've really got to keep track of where all your frames are pointing, especially when you get to big like multiple degree of freedom linkages. Okay. So continuing there, when you go into it, you select force. It's going to create another port, and this is actually a different port. It's not a Simulink port. It's not like the frame ports we've seen with Simscape Multibody. It's called a PS port, so you need to get this weird block called a Simulink PS converter, and they've got a backwards one as well. It basically just like takes a number from Simulink, turns it so that it can be read into that, and you're set. Yeah, so what will happen here is it's a step input. Like I said before, step inputs are pretty much always what you use if you're ever inputting something to a system. Again, just to change the 1 to negative 500, because that would be 500 newtons in the negative x direction, which we defined here, which will push it towards the other ball. Okay. Oh. Motion outputs. Just like we kind of had the input set up here, you can also set up outputs. So I only sense position, but you could sense, velocity, acceleration, actuator force, all that stuff. And I have them coming out of both these joints here with the PS to Simulink converters into a single graph scope, into a single scope. The scope has 2 inputs. Like I said before, there's a block called mux, which basically combines signals into a single signal. But this is just as fine. The other thing being, I changed the input here. It looks a little complicated. It's basically just it's applying the force from 0 to 5 seconds and then stops. That way, we're not keeping applying force after it collides, because that would be it wouldn't be easy to see what's happening. Okay, so now we ran the simulation. We got out of our scope the position of the 2 balls, the blue one being ball 2, which is being pushed by the force, and then the yellow one being ball 1, which is stagnant until they collide. So I can run this simulation here. I ran it for 30 seconds. So it's like, these are really heavy balls also. That was like probably a mistake. But you can see they collide pretty well. Or at the very least, like they collide exactly as you'd expect them to. So yeah, the second, or I guess the third, the one that's like 2 balls complete, is basically up to that point, where if you run that, you will get this simulation, where you've got the ball colliding into the other ball, and it outputting the simulation and also the position. So, playing with the simulation. I mean, you've got a simulation that works. It's two balls colliding. So, if you want to play with it, it's so easy to kind of see how the numbers kind of affect the results of the system. You can change the size, the density of the ball just by changing a single number. You can change the input force, you can change the type of force, the length of time it goes for, the magnitude. You can input velocity instead of force and see how that affects it. You can also record your acceleration and velocity values, all sorts of other values. There's so much information you can get out of this small system. The only thing it really takes is just kind of setting up the system in the first place so that all the objects can interact the way they're meant to. And so, yeah. Any questions on, yeah. That was the little collision simulation. It's not a super complicated one, to be honest, and that's why I did it. But I tried to go really in depth with what every single block was doing, because to be honest, none of the notes that we've had in class have done a good job of that. And you're really going to see that next, because the linkage, honestly, I was a little strapped for time. I ended up just grabbing and taking a bunch of stuff off of a linkage that I've made for class. It's an RRRP linkage, which is it's a crank slider. Effectively, you have an input, which is a rotational thing, and your output is a slider. It looks like this. That's what the simulation looks like. When you take dynamics of machinery, your project is usually something like this. It's usually some sort of linkage. So, it's really messy. Please do not even attempt to like look at this format and be like, oh, I'm gonna do something like that, because no, it's bad. I don't like it. Everything about this format is bad. But you can see with the format exactly where all of the joints are. And these cylinders, they don't have to be here. It just kind of makes it a little bit easier to visualize where the joints are. But we can see here, fixed frame A4, that's kind of the invisible bit. A1 is kind of this first linkage, or this first link rather. A2 is the second link, and then A3 is the slider. How they're connected, only by two joints. And the slider has this prismatic joint to the frame, to the world frame. So that way it can slide along that world frame, and it can rotate around link A2, but it's stuck to move in those two things. And it's stuck to move as a result of the input given here at crank A1. Also, we're pretty much nearing the end of what I have prepared. So I just want to go in a little bit more explanation as to what I'm trying to get at here. So you have a pretty complex linkage. Synthesis of this stuff takes a pretty long time to do by hand. Setting this up, once you know how to do Simulink, you can do it in probably 20 minutes. And then you're set to just change whatever values as much as you please. But more importantly, you can specify inputs at any point, and then observe the outputs at any point. So as part of this project here, we were having to put an input at this one, watch the output that was output at the slider, Obviously, it's going to be a pretty complicated number to know exactly how much torque you're doing here and how much force that responds to at that point over time. Well, with this, you can just look directly at it. It just generates it for you. You save a ridiculous amount of time. It's crazy. Just by setting that as your output. But also, okay, so this is why I love it so much. Because you have a specified input that you need to input into here. And you have from your output a speed, an acceleration, a position, a force even if you need it. These can be used for feedback for a control system just immediately. Because you have what's called here, it's called a plant. It's basically one big, in mechatronics, this would just be one big transfer function. But you don't have to do that in Simscape because you can just play with blocks and plug them in together. And all of a sudden, you can plug an input right in. You can hook it right up to the PID tuner. And you have a straight up control system. So basically, like, you have the ability to make pretty complex robotic control systems with this really, really quickly. Which, many of you might not even touch at all. I don't know, but I think it's really cool. So I like sharing that. Okay. Straight up, that is the end of my slides. I kind of rushed through. I don't want to like... I honestly don't entirely know what I was planning to do going forward from that. But I'm sticking around either way in case people legitimately need help with Simulink, because I'm pretty okay at it. If you have questions, feel free to add me on Discord, because I have just a compulsive need to help people when they ask. You can email me as well. I'm going to have to fix that slide. Anyways, yeah. Thanks for coming out, hopefully learning stuff. Even if you didn't, maybe you can enjoy just, running the simulation. It's kind of fun to watch. But, yeah.